Hi folks, we're starting to look at electron configurations, and electron configurations are going to be more complicated in Chemistry 1 than it was in physical chemistry, physical science or middle school science. Our electron configurations are going to be based off of the quantum mechanical model of the model that we learned about earlier. And just as a quick refresher, we have 4 quantum numbers that specify the address of each electron in an atom. And no 2 electrons can have the same address. They each need a different set of 4 quantum numbers. Those 4 quantum numbers are the principal quantum number, which tells us what main energy level we're in. Are we here close to the nucleus, or are we a couple of energy levels away from the nucleus? The angular momentum quantum number tells us what sublevel we're in. These sublevels have characteristic shapes, and we call those S, P, D, and F. Remember, we need to know the shape of an s orbital and a p orbital. S orbitals are just spheres, and p orbitals are dumbbell-shaped. The magnetic quantum number tells us the orbital orientation. And depending on what shape your orbital is, you can have a different number of orientations. For instance, when you have a sphere, there's only one way to orient that sphere on the axes. But if you have a p orbital, you can have it along the x-axis, you can have it along the y-axis, or you can have it oriented along the z-axis, kind of sticking out of the page at you. So those are the 3 p orientations, and then D has 5 orientations, and F sublevels have 7 orientations of their orbitals. And lastly, the 4th quantum number is the spin quantum number, which tells us the electron spin. Again, just as a quick overview, quantum number L depends on N, and then quantum number M depends on L. So in the first energy level, we can only have one kind of sublevel, but in the second energy level, we can have S and P sublevels. And then in the third energy level, we can have S and P and D. So each time we go up a main energy level, we can have more types of sublevel. And then each sublevel has its own characteristic number of orbital orientations, as we said before. The main energy level, N, actually tells us the number of sublevels that you can have per main energy level. And N squared tells us the number of orbitals you can have per main energy level. So for instance, 2 squared is 4, and notice we can have 1, 2, 3, 4 orbitals in that sublevel. 4 squared is 16, and if we count, we should have 16 orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you can predict how many different orbitals you have at different levels. Quantum number S does not depend on anything. There are going to be 2 electrons per orbital no matter what the shape is, no matter what energy level you're in, no matter what the orientation is. So these electron configurations. Electron configurations are a method for showing the arrangement of electrons in a particular atom. As I said before, in physical science or in middle school science, you learned how to place, this is called the Bohr model, this picture that I have here. You learned how to place electrons in rings, and you only needed to show what energy level the electrons were in. Not anymore. We're going to get more complicated than that now. But we are still going to base our electron configurations off of energy levels. It's just that we're going to go even deeper into detail. We're going to talk about energy levels as well as the sublevels and orbitals that electrons are in. So here are a couple of examples of electron configurations. There are different styles of electron configurations, but for instance, here we've got orbital diagram, and here we've got electron configuration. Notice that we are labeling this with 1s, 2s, 2p, 3s, and we're doing the same thing here, 1s, 2s, 2p, 3s. So these electron configurations are more detailed than that Bohr configuration that we had on the previous slide. Although there are different styles of electron configuration, they all follow the same 3 basic rules. So let's talk about what those rules are. The first rule is the Aufbau Principle. Electrons always fill the lowest available energy orbitals first. If you look at this diagram, we've got low energy down here. Low energy is low. High energy is up high. And if we look at the lowest energy, 1s is way down here by itself, so that's definitely the lowest energy. Then we seem to have 2s and then 2p. Then we seem to have 3s, then 3p. But the next one up isn't actually 3d. If you look, 4s is just slightly lower energy than the 3d is. That means that once we start filling up these energy sublevels, they stop going in a nice convenient order. It would be really nice if the order were 1s, then 2s, then 2p, then 3s, then 3p, then 3d. But that doesn't happen. We start getting overlap right here. So that means that after argon on the periodic table, the electron configuration starts getting a little bit more complicated. So 3d comes after the 4s. So that's a little surprising because 3p, then a 4s, and then a 3d. And then when we get up really high, we go, when we've got 6s, then we go back to 4f. Notice that the 6s is lower in energy than the 4f. And then the 5d, and then the 6p. This is going to make finding the correct order for energy sublevels a little bit complicated, but there are a few tricks to help you remember the right order to put electrons in, and we'll talk about that momentarily. But before we get there, I just want to point out that whenever there are multiple orbitals in a sublevel, and that's true for p and d and f sublevels, then those orbitals have the same energy and they fill at the same time. So notice here, this D sublevel, I've drawn all 1, 2, 3, 4, 5 orbitals in the D sublevel connected together because they all have the same energy and they're going to fill at the same time. So that is a summary of the Aufbau Principle. Now, to help you remember that order, I promised you a couple ways to help you remember it. The diagonal rule is a helpful tool to help you remember orbital filling order. However, if you choose this rule, you do have to memorize it. You have to be able to recreate this diagram that I'm about to show you. I personally prefer a different method, but different methods work better for different people. So let me explain the diagonal rule for you. First, you write the numbers down 1 through 7. Next, you write an S next to your first energy level because the first energy level only has S electrons. Next, in the second energy level, you can have S sublevels and an S sublevel as well as P sublevels. So we have the 2s and then we have the 2p. Remember, in the third energy level, you can have S or P or D electrons. When you do this, it's super important to keep your S's lined up with each other and your P's lined up with each other and your D's as well as your F's, which are coming next. In the fourth energy level, you have S and P and D and F. In the fifth energy level, you have S and P and D and F. Could there be G sublevels? Yes, maybe. If we ever discover an atom that has that many electrons. We never actually get that far, or we haven't gotten that far for any known elements, and you'll see why this is in a moment. Similarly, with energy level 6, you can go up to the letter H, possibly, and in energy level 7, you can go up to the letter I. Okay, so how do we use this diagram to help us remember the correct filling order? This is called the diagonal rule because if you start drawing diagonal lines, like so, through the different energy sublevels, it will tell you the correct filling order if you start at the top and work your way down. So first comes 1s, then comes 2s, then comes 2p and 3s, then comes 3p and 4s, then comes 3d, 4p, 5s. Then comes 4D, 5P, 6S. Then comes 4F, 5D, 6P, 7S. Then comes 5F, 6D, 6P. At this point, we have used, we're past the current periodic table, so we can stop at this point. So we don't keep on drawing diagonal lines. We never have to use this G, or we never get up to 6F or 7D, just because with the number of electrons you can place in these energy sublevels, you never get up this high. So be sure to add those diagonal lines to your notes because they don't tend to print clearly. So just make sure, and also it gets you in the habit of learning how to draw and reproduce this diagram if this is how you are going to, if this is the method you're going to rely on for doing your electron configurations. I have a method that I prefer, which I'm going to just briefly introduce you to now. My way I call reading the periodic table. There are a few things you have to memorize also with this method, but you're always allowed periodic tables on tests, and so this is how I like to think about it. The first thing you need to remember is that helium, we put helium over here because helium is not very reactive. It has a full valence shell, and therefore we group it with the noble gases. However, it's actually in the S block, so you could kind of think about helium as being over here on the periodic table. So that's one thing you have to remember for my method, is that helium is here in the S block. You do need to remember that this is the S block, this is the P block, this is the D block, and this is the F block. Okay. And you need to notice that the S block is 2 elements wide because it can contain 2 electrons. You need to notice that the P block is 6 elements wide. It can hold 6 electrons. The D block is 10 elements wide. It can hold 10 electrons. And the F block, although there are 15 elements drawn down here, 2 of those elements actually belong in the D block. But these remaining 14 elements are an indication or a reminder that the F block can hold 14 electrons. Remember, we have our periods numbered on the periodic table. So this is period 1, 2, 3, 4, 5, 6, 7. The lanthanide series is actually here in period 6, and the actinide series is actually here in period 7. What we do now is we read the periodic table. There is one more rule I need to show you, but for right now I just want to show you how this starts. We read the periodic table to get the correct order for the electron configuration. So for instance, the 1s comes first. The 2s comes next. The p comes next. The 3s comes next. The 3p comes next. The 4s. Okay, here is where the last thing that you need to remember comes in when you're using this method. Notice that so far our period number has corresponded exactly to our energy level. That's true for the S block and the P block. But when you get to the D block and the F block, that is no longer true. When you're in the D block, you have to subtract 1 from the period to get the correct energy level. So this is not the 4D sublevel. This is the 3D sublevel. Similarly, this is the 4D sublevel. This is the 5D sublevel and the 6D sublevel. You always subtract 1 from the period to get the energy level. There's a similar rule for the F block, except this time you don't subtract 1, you subtract 2. So even though the lanthanide series is in period 6, we call this the 4F sublevel. This is in energy level 4. These F electrons are in energy level 4, and this is the 5F energy level. So if we continue with our numbering, now that we know these rules, this will give us the correct order the same way that the diagonal rule did. So after the 4S comes the 3D, then the 4P, so this was the 3D, the 4P, then comes the 5S, then the 4D, then the 5P, then the 6S. Now, look, we have to look down below at the lanthanide series. The 4F, the 5D, the 6P. I'm just going to erase this label here so that I have a little bit room for all of my sublevels to write down. After the 6P comes the 7S, then the 5F, then the 6D, then the 7P. So you can see I end up using this method, I get the same order of energy sublevels that I did using the diagonal method. Both methods require memorizing something. I personally prefer this method. I think it allows you kind of to take certain shortcuts, especially if you continue on with chemistry, but you can use whichever method so long as you learn your method. Okay, we just spent a lot of time talking about the Aufbau principle, where we're always filling the lowest energy level that is available first. I told you that there were 2 other rules we had to talk about, so let's look at those other rules now. The Pauli exclusion principle says that no 2 electrons in an atom can have the same 4 quantum numbers. Therefore, if 2 electrons are in the same orbital, they must have opposite spins. They must have opposite spins. We're going to be drawing some electron configurations where we draw each orbital as being represented by 1 box. And then when we draw electrons in that box, when we draw electrons in that orbital, to represent these opposite spins, we draw arrows going opposite directions, an up arrow versus a down arrow. So each arrow is 1 electron, so just make sure you add that to your notes. The up arrow represents a spin of positive 1/2, and the down arrow represents a spin of negative 1/2. The third rule you need to know about is called Hund's rule. And this rule states that when there are multiple orbitals in a sublevel, whether it's p or d or f, you have to place one electron per orbital before you start pairing the electrons. This rule is also called the empty bus seat rule, because if you think about choosing seats on a bus, if there are these kind of two-seater seats and there's some random person sitting here that you don't know, you are probably going to choose a totally different seat to sit at before you choose this seat. You'll only choose this seat next to a random stranger as a last resort. You'll go choose your own seat first before you sit next to somebody you don't know. And electrons do the same thing. So in this example with p sublevels, where we have 3 orbitals in a p sublevel, if we have to put 4 electrons into that p sublevel, this would be the wrong way to do it. Okay, we don't pair up the electrons until there's no other choice. The right way to place those electrons is electron number 1, electron number 2, electron number 3, and now start doubling up the electrons because there's no other choice. All the empty seats on the bus have been taken, and now we start doubling up on the bus seats. Notice that all of our arrows go the same direction. All of the arrows, all the electrons have the same spin until we start doubling up the electrons. That's when you start introducing the electron with an opposite spin. Okay, the s sublevel, we've talked about this before, but we're going to use it a lot today, so just as a reminder, the s sublevel has 1 orbital. Each orbital can hold 2 electrons, and 1 times 2 is 2. So the s sublevel can hold 2 electrons. The p sublevel has 3 orbitals. Each orbital holds 2 electrons, so the p sublevel total can hold 6 electrons. The d sublevel has 5 orbitals. Each orbital can hold 2 electrons, so total the d sublevel holds 10 electrons. And the f sublevel has 7 orbitals. Each orbital can still hold 2 electrons, and so the f sublevel holds 14 electrons total.